Hi there. Welcome to the Organic Chemistry Reaction Rules simulation. Here you will learn all the basics about how organic compounds react with each other, including key concepts like electronegativity, nucleophiles and electrophiles, leaving groups and lone pairs. So buckle up, we're going on a reactive journey together. This simulation uses voiceovers. Using the lab pad is an important way to get the most out of this simulation. Is this the first time you are playing a Labster simulation? Perfect. Then let's get started with your first mission. Find the lockers and open one of them. Raise your lab pad for more and find a lab coat inside the lockers and pick it up. Enter the lab. Alright, let's start with a question. What is electronegativity? Yes, great start. Electronegativity is a measure of an atom's affinity for electrons. You can see the electronegativity of all the elements on the periodic table on the wall. Click the right arrow beside the periodic table. Look at the periodic table on the wall. Organic chemistry has carbon as the main character. That's why it is emphasized here. As a rule of thumb, all the metals are less electronegative than carbon, whereas the non-metals are more electronegative. There are a few exceptions to the latter, as you can see. Click the right arrow on the periodic table. Look at the periodic table on the wall. Learning all the electronegativities by heart seems impossible, but it is also quite unnecessary. As you can see, organic chemistry actually only deals with a few of the elements, so these are the ones you need to concern yourself with. You may wonder why we are talking about electronegativity. Well, it is an important concept in organic chemistry because it is a very useful tool in assessing whereabouts in a molecule there is a high electron density, and where there is a low electron density. Electrons are the currency of chemistry, and every time a reaction occurs there is some kind of transaction of electrons between atoms. Recognizing the position of electrons is the first step in figuring out what will happen in a reaction. What are covalent bonds? Exactly. In a covalent bond, the two bonding atoms each donate one electron to an electron pair that is shared between them. This is different from an ionic bond, where one atom donates an electron to the other atom, thus creating a cation and an anion. Even though the atoms share the electron pair in a covalent bond, it is not shared equally between them, not unless they have the exact same electronegativity. The element with the highest electronegativity will exert the strongest pull on the electrons of the shared bonds, and thus the electron density on that atom will be higher than the electron density on the neighboring atom. We say that the bond is polarized. Let's go to electronegativity hollow table on your left. Alright, this is your first challenge. You can see an arrow that represents increasing electronegativity. Your task is to sort molecular bonds by placing them on the arrow according to their polarity. The molecules placed on the right end of the arrow will be the ones with the highest polarity. You can hover over each section of the arrow to see which polarity it represents. Let's try placing the CC bond first. We know that the polarity of the CC bond is about 0, because it's a bond between two atoms of the same element. Splendid. Let's do the other one as well. To determine the difference in electronegativity, simply calculate the difference in electronegativity between the two values for each atom. The electronegativity values of all atoms can be found in the periodic table. I have prepared one for you in the Media tab, which you can use to help answer these questions. Great! As you can see on the hollow table screen, a Done button is activated after you've placed all the molecular bonds on the arrow. Click on it to check if the molecular bonds are correctly placed. Press Done to check it. Great job! Your answer is correct. You are ready for the next challenge. Nice progress. The absolute value of the difference in electronegativity provides a rough measure of the polarity of the bond. You can estimate the type of bond from the difference in electronegativity. Generally, below 0.4 gives a nonpolar covalent bond, between 0.4 and 1.7 a polar covalent bond, and above 1.7 is considered an ionic bond. Great job so far. Take special note of the check out the tooltips of the molecular bond. Are you ready to continue? Alright, let's see if you can answer a quick question about the bonds. Which of the following molecular bonds is the most polar? Indeed, having an OH bond in an organic compound makes it more polar overall. Electronegativity is one tool for determining the electron density in different parts of organic molecules. Other important things to look at are the location of charges, lone pairs, and pi electrons. Now you should try to apply all of these concepts and see if you can use it to predict the outcome of a reaction. Let's move to molecular visualization hollow table on your right. Here you see two molecules, one bromo-but3ene and a hydroxide ion. Let's explore their formal charges, lone pairs of electrons and electron density. The first thing we are going to look at are the formal charges. If an atom bears a negative or a positive charge, it will have a big impact on the electron density of that molecule. But be careful when you look at molecules which have formal charges. The actual charge is not always located on the atom you think it is, and sometimes it is spread out over several atoms. Assign the correct formal charge for each atom. Wonderful. Now click on the whiteboard. On this whiteboard, you can see a 2D representation of what's going on at the hollow table. Check it out each time you make changes on the molecular visualization hollow table. The next thing we need to look at is where the lone pairs are. A lone pair is a pair of electrons that do not partake in bonding. To count how many lone pairs an atom has, you need to know how many valence electrons that atom has, and how many bonds. It uses one electron for each bond, and the remaining valence electrons make up the lone pairs. Place lone pairs around the atoms. Click Done to check if it's correct. Great job. We will now look at partial charges. This is where the difference in electronegativity and the polarized bonds come into play. You will see little green arrows above the bonds that represent the direction of the polarity. Designate the polarity of the molecules. Click Done when you think you've got it. Splendid. The last thing we need to identify is if there are any bonds that have pi electrons. Pi electrons are present in double and triple bonds, and they are important because the electrons in pi orbitals have a higher energy level than electrons in sigma orbitals. It means that the pi electrons are easily broken, either to form new bonds or to place a negative charge on one of the bonding atoms. Identify the pi bonds. You're a genius. You have located all the key factors in determining the electron density of the different parts of the molecule. If you press the play button, you can see a visual representation of the electron density around the molecule. But before you do so, try to see if you can guess where the electron density will be highest and where it will be lowest. An electron density map describes how the charge of electrons is distributed. Red indicates a region with high electron density and blue indicates a region with low electron density. Press the play button to see the electron density cloud around the molecules. The visualization of electron density is also known as an electrostatic potential map. It's a very nice tool for visualizing the electron densities if you're performing detailed calculations. But for practical purposes, it is better to just have an idea about the relative electron densities and then use that to locate the main characters of the reaction, the nucleophiles, electrophiles, and leaving groups. A very important role in any reaction is the nucleophile. Nucleophilic means nucleus loving. The nucleophile has electrons to spare, money to spend. So this is where the reaction begins. Good nucleophiles have fast reaction rates in nucleophilic addition or substitution reactions. There are three key factors that influence how nucleophilic a species is: charge, electronegativity, and size. Let's go learn more about that. Go to the organic chemistry workbench. At this workbench, you will learn about nucleophiles, electrophiles, and leaving groups. First, the nucleophile. You will interact with the screen on the left side of this workbench to determine which species is a good nucleophile. There are 3 tabs on the screen that you will need to complete. I'm sure you can do this. Pick which are the better nucleophiles of these pairs. Click the question mark to change it to a larger than or smaller than sign. Click the Done button when you think you have it. On the left screen in all 3 tabs, choose which atoms are better nucleophiles than the others. Yes, you got it. The negatively charged species is the stronger nucleophile in all the cases. That is because they have a higher electron density than their neutral counterparts. Order these 4 species in increasing nucleophilicity. Click the nucleophiles to pick them up and then click the place in the row where you think it should go. Click the Done button when you think you have it. That was quite the opposite of what you would expect, right? The highly electronegative atoms hold onto their electrons so tightly, so even though they have a high electron density, they are not the most nucleophilic. Let's see if you understand the concept of the leaving group. This time we will use the screen on the left side of the workbench. Click on the lab pad for more information. Sweet. Actually, basicity is a subset of nucleophilicity, where the nucleophile donates electrons specifically to a proton. It can actually be difficult to decide whether a species will react as a base or a nucleophile in a given reaction. There is also a 4th factor which is very important in determining how strong a nucleophile is, and that is solvency. This factor will be covered in another simulation, but if you are curious now, then you can read a bit about it in the theory pages. Another very important role in a chemical reaction is the electrophile. Electrophilic means electron-loving. This is where the nucleophile will react. If we stay in our money analogy, the nucleophile has money to spend, but the electrophile has something to sell. An electrophile will accept an electron pair, just like a Lewis acid will. When identifying the electrophiles, remember that just like nucleophiles are also bases, look for factors that make the species acidic. Let's try it now. Which of the atoms marked in blue is the most electrophilic? Yes, you got it, but that was a tricky one. Even though the formal charge is located on the oxygen atom, the most electrophilic part is actually on the carbon atom. One reason for this is the fact that the oxygen atom is more electronegative than the carbon atom. When some of the electrons around oxygen are used to bind the proton, then the electrons in the CO double bond are pulled more towards oxygen than otherwise. This can also be explained with a concept called resonance. Go to the theory pages if you want to learn more about resonance in chemistry. Alright, as for the nucleophiles, an important factor for electrophiles is electronegativity. Being bound to something which is highly electronegative makes an atom electrophilic. Look at the molecule on the small hollow table in front of you. See if you can pinpoint where the molecules I showed you are most electrophilic. Place the blue sphere on the most electrophilic part of the molecule. That's correct. Let's try one more. Wow, you did it again. Carry on. You got it. Let's see if you figured out a few basics about electrophiles. Describe the electron density around electrophiles. Exactly. Electrophiles are areas in a molecule that have a relatively low electron density. In chemical reactions, what role do electrophiles play? Bingo! Because electrophiles have a low electron density, they readily accept electrons from nucleophiles to form new bonds. Okay, the third thing we need to identify in our quest for understanding reactions in organic chemistry is, what makes a good leaving group? A leaving group can be thought of as a nucleophile working backward. It leaves the molecule, breaking a bond and taking a pair of electrons with it. So contrary to when we looked at nucleophilicity, we now want a species that is happy to have a high electron density around it, for example an element that is highly electronegative. Can you think of another factor which would give a good leaving group? That's right, weak bases are good leaving groups. But how can we explain that? To understand why, consider the reaction below. The molecule on the left is called p-toluene sulfonic acid, or just tosylic acid, which is a strong acid. Strong acids dissociate completely to give the corresponding base and a proton. They do so because the negative charge is well stabilized in the corresponding base. And the corresponding base of a strong acid is a weak base. In other words, the stronger the acid, the more stable the corresponding base when acting as a leaving group from the proton. And that is exactly the same as when acting as a leaving group from another molecule. So when considering how good a leaving group something is, think about its corresponding acid. The stronger the corresponding acid, the better the leaving group. I think you are ready now to look at some leaving groups. In the next challenge, you will sort 5 species based on how well they would react as leaving groups. You will use the screen on the right side of this workbench. Place each species according to its reactivity as a leaving group. Great job, your answer is correct. You are ready for the next challenge. Marvelous work. So once again, what is the key factor for a good leaving group? You've got this. Weak bases are good leaving groups. Okay, let's head back to the molecular visualization hollow table and look at our 2 reactants there. Go to the molecular visualization hollow table. Alright, see if you can use what you have just learned to locate where the key parts of this molecule are. Place the spheres on the molecules to correctly identify the leaving group, and nucleophilic and electrophilic regions. Fantastic work, genius. Now let us go back to our money analogy from earlier. If electrons are the currency, and reactions the money transactions, then reaction mechanisms are like the accounting system that keeps track of the money flow, the flow of the electrons. How exactly is the reaction taking place? Where are the electrons moving between? The very short answer is that the electrons will move from an area of high electron density to an area of low electron density and form a new bond. However, that is not all there is to a reaction mechanism. Sometimes you need to break bonds and move charges around. But don't worry, you can keep track of everything by using the brilliant accounting system presented to you by the curly arrows. There are 3 different types of curly arrows. Let's see if you can recognize the different types of arrows. Click on the big wall screen. Arrange the mechanistic steps according to their category. Focus only on the blue arrows. Great job, your answer is correct. Very cool. I have added an image of the correct arrangement in the Media tab. It's time now to look at the reaction at the hollow table again. Click on Molecular Visualization Hollow Table on your left. Look at the molecules at the hollow table. You need to figure out how they will react. You have already identified nucleophilic and electrophilic areas of those molecules. As you can see, there are 2 different nucleophilic areas in play, so you need to decide which one is the stronger nucleophile. Click the strongest nucleophile on the hollow table. Yes, you are absolutely right. The negative charge on the oxygen atom makes it the stronger nucleophile. Now where do you think it will react? Click the atom that will be attacked by the nucleophile. Yes, that's the one. Let's see how it works. Cool. The nucleophile attacked the electrophiles, and a new bond has been formed. But look out. You are about to create a carbon atom with 5 bonds. You have to break a bond to complete the reaction. Pick the bond on the molecule you think will break to bring the reaction forward. Right on. The bond to the leaving group will break and the leaving group will do what it does best, leave and take the electrons with it. Amazing. You've completed the reaction. What type of reaction do you think it was? Yes, well done. It is a substitution reaction because one part of the molecule has been substituted for something else. Generally, reactions of organic compounds are divided into 3 main types: additions, eliminations, and substitutions. Let us look into these reaction types in a little more detail. You can see them on the large screen. Click on the big wall screen. Okay, so in addition reactions, a new part is added to a substrate molecule, but no part of it is broken off. For this to occur, the molecule needs to have a double or triple bond, like in alkenes or carbonyl compounds. Check out the theory pages if you need to brush up on the functional groups. As you can see on the screen, addition reactions are divided into 2 subclasses, nucleophilic and electrophilic, based on whether the substrate reacts with a nucleophile or an electrophile. I will challenge you now to fill in the empty fields on the screen on your own, and then follow up with some points about the other reactions. I'm sure you've got this. Complete the overview by filling in all the boxes with question marks. Amazing work. I want to clap, but could you give me a hand? Okay, in a substitution reaction a bond is made and a bond is broken. That means that one of the main requirements for a substitution reaction to occur is that the substrate contains some form of leaving group, like the bromine atom of the bromobutene you saw on the hollow table. Substitution reactions, like addition reactions, are divided into subclasses based on what type of substrate is involved. Nucleophilic, where the new substituent is a nucleophile, and electrophilic, where the new substituent is an electrophile. The nucleophilic substitution reactions can furthermore be divided based on substrate type. SN1 or SN2, which are substitutions directly on an sp3 hybridized atom, and then those which are substitutions on an sp2 hybridized atom, like a carbonyl carbon. What specific type of substitution reaction do you think you completed on the hollow table before? That's right, the substitution took place on an sp3 hybridized carbon atom. In an elimination reaction, no new bonds are being formed in the substrate, but bonds are broken. This results in the formation of a double bond or a charged species. For an elimination reaction to occur, the substrate needs to have some kind of leaving group, so the substrate could be the same as for a substitution reaction. Actually, the reaction conditions for performing an E1 or E2 elimination or an SN1 or SN2 substitution are very similar, and you will often find them to be competing reactions under the circumstances. But that is a topic for another simulation. That's it for now. We've been through the core concepts for reactions in organic chemistry. But this is just the beginning. So much more exciting chemistry lies ahead, where we can use these concepts in wonderful, and sometimes complicated, reactions. Good luck on your continued chemistry journey. Let me ask you one last question. Do you feel like you gained relevant knowledge during this simulation? Thank you for your feedback. Your score has been saved together with your 100% progress. Congratulations, you have completed the simulation. We hope you enjoyed it and you feel wiser now.